So good evening. Today we'll discuss about spread spectrum communication. So what do you mean by spread spectrum communication? So till now we studied a number of modulation techniques, and all modulation techniques are used for efficient utilization of power and bandwidth. There are some other applications, so we are not bothering about the bandwidth, right? So let us consider some applications where we need to transmit the data more securely. That means, so we need to transmit the data. That data has to resist to the external interference, and it make very difficult for any unauthorized receiver to receive the data. Now such type of communications, we are calling it as the secured communications, and this secured communication is possible by using a modulation technique called a spread spectrum modulation technique, right? So the major intention for spread spectrum communication is that so we need to transmit the data more securely. So where we are using this spread spectrum communication, as I'm saying, so we are transmitting data very securely. The primary application of spread spectrum is we are using in military communication. So generally the spread spectrum communication is developed during the World War II for secure transmission of data from one point to the another point. So we can also use this spread spectrum communication in non-military applications to avoid interference and jamming. So what do you mean by interference? Let us assume that I'm having a channel, right? I'm having a channel. So this is my channel I'm having here. So if more than one user are transmitting the data through the same channel at the same time, that will cause an interference. To avoid such interference, we use spread spectrum communication. So another major intention for using spread spectrum communication is to avoid jamming. In some application, some of the unauthorized users, they intentionally creating an interference so that the transmission can be blocked. Now such type of communication we are calling jamming, right? So to avoid jamming, we use spread spectrum communications. So what is the definition of spread spectrum communication? So we are dividing the definition of spread spectrum communication into two parts, right? The first part is that we are transmitting the data. That data will occupy a more bandwidth than a minimum required bandwidth, right? That means, so we are having a narrowband signal. Now that narrowband signal we are representing over a wide band. So in order to convert a wideband signal, we are using, that means we are spreading the spectrum. That means we are increasing the bandwidth at the transmitting end, and whatever the amount we are increasing, the same amount we need to decrease, that is de-spreading at the receiving end. So this can be done by using a special code, and those codes we are calling a spreading codes, which are independent of data sequence. Let us see, I'm having a narrowband signal here. So this is my narrowband signal, which is the bandwidth of the signal. This signal I'm applying to the spread spectrum system with a spreading code. So what is the job of this spread spectrum? That will distribute this narrowband signal over a wider bandwidth, right? I'm distributing over a wider bandwidth with the help of the spreading codes. So I can call this signal is a wideband signal, which is occupying more bandwidth than the actual required bandwidth. Even though the problem here is the bandwidth is increasing, right? So we are not bothering about the bandwidth. So our intention is to transmit the data as securely as possible, right? Now, let us see what are the advantages of this spread spectrum communication. As I am saying, once we are converting a narrowband signal into wideband signal by applying a spreading codes, these wideband signals appears like a noise-like signals, and it is very difficult for any unauthorized receiver to receive the data because the signals are appearing like a noise signals. So it's very difficult to detect and intercept. So that is a first advantage of the spread spectrum communication. And the second advantage is it eliminates multipath interference, right? And the third one is that it transmits the data more securely by using a special codes and spreading codes. Those codes we are calling a pseudo random sequence or a pseudo noise sequence. So this is the one form of the spreading codes. And the another advantage is it avoids jamming. So what is the disadvantage? As we know that the bandwidth is increasing. So that is the drawback of the spread spectrum communications. So what are the major applications of the spread spectrum? As we know, we are saying secure communication we are using in the military. So we use in 3G or code division multiple access. We use in wireless LANs and we are using in global positioning systems. GPS. Right? GPS. So what are the types of the spread spectrum communication? There are majorly 4 types of the spread spectrum communication. They are the first one, direct sequence spread spectrum. We are calling it as DSSS. The second one is frequency hopping spread spectrum. In short form, we can call it as FHSS. Time hopping spread spectrum, and the hybrid method. The combination of any of these 3, we are calling it as hybrid methods. Right? Now we'll see what is the major block diagram of the spread spectrum communication. So this is a major block diagram of spread spectrum communication. So as we see, we are having channel encoder in the transmitter. We are having channel decoder in the receiver. So I'm having a modulator, right? So one of the input to the modulator is a pseudo noise sequence, is a spreading code, right? And we are using this pseudo noise sequence in the transmitter as well as in the receiving end, right? So initially I'm having the information sequence. As we all know that the channel encoder will add additional bits to the information sequence. For example, I'm having a sequence like 101010, for example. So this is my binary data sequence. So whenever I'm applying this binary data sequence to the channel encoder will add additional bits to the incoming binary sequence. So what happens when I'm adding extra bits to the incoming sequence? By using these extra bits at the receiving end, right, in the channel decoder, it is possible to detect if there is any errors in the received sequence, and it is also possible to correct those errors by adding these extra bits. So that is a major job of the channel encoder, right? So the output of the channel encoder, let's call it as a coded sequence, right? So it is a coded sequence. So I'm giving a coded sequence as an input to the modulator. The another input to the modulator is a PN sequence generator. It's a spreading code. Now the modulation technique I can use here is a direct sequence spread spectrum, or it is a frequency of spread spectrum, or it may be a time hopping spread spectrum, right? So whatever the modulated, whatever the coded sequence, that is varied in a pseudo random manner. Thereby it produces any one of this modulation, right? It may be direct sequence, frequency of, or timing of spread spectrum. Now this modulated data we are transmitting through the channel. Due to the noise in the channel, the transmitted bit maybe goes to errors. So the input to the modulator is a narrowband signal, right? So whenever I'm applying a pseudo noise sequence to a modulator and a narrowband signal, this narrowband signal is converted to the wideband signal, right? So this wideband signal I'm transmitting through the channel. The input to the demodulator is a modulated or a wideband signal. So in the transmitter we are spreading the signal. So in the receiver we need to defree the signal. So the wideband signal I'm giving here. In the demodulator, it will again I'm using PN sequence generator, so that it will perform the reverse operation of the modulator, so that this wideband signal again converted to the narrowband signal. This narrowband signal I'm giving to the channel decoder. It will perform the error detection as well as correction, so that finally we will receive the binary data, right? So this is a simple block diagram for the spread spectrum communication. Now let us see what is this pseudo noise sequence, what is this spreading sequence, right? So let us see one of the case of this spreading code that we are calling a pseudo noise sequence, right? A pseudo random sequence, or simply we can call it as the PN sequence, right? Now this PN sequence is a noise like high frequency signal, right? And which is in binary in nature. The PN sequence binary in nature and is a high frequency signal and looks like a noise signal, right? So why we are calling it as pseudo random? Why we are calling it as pseudo random, right? So this sequence is not completely random and is not completely deterministic, So we can call it as a pseudo random. So this sequence, I'm saying a pseudo random, which is defined by using some logic in the transmitter. Whatever the logic you're using in the transmitter, the same logic we need to repeat in the receiver section. So if you know the logic, it is possible to generate the PN sequence in the receiver section, whatever the PN sequence I'm using in the transmitter. Let us see how we generate this PN sequence. This PN sequence can be generated by using a linear feedback shift registers, right? And by using a combinational logic. As we know that in the shift registers, we need to use a flip-flops, right? Let us say a block diagram, a generalized block diagram for a PN sequence. Here I'm using small m number of flip-flops. These all are the flip-flops I'm using here, right? Let's say I'm using here small m number of flip-flops. In order to move the content of one flip-flop to the another flip-flop, we are applying a clock signal. Whenever a clock is applied, the data of one flip-flop is moved to the another flip-flop. That is the reason we are using here a clock signal. As I'm saying, it is a linear feedback shift registers. So in this case, we are not using any external input signal. So we are using here some combinational logic. The output of the combinational logic, I'm taking it as an input to the first flip-flop. And the output of the first flip-flop, I'm giving to the next flip-flop whenever I'm applying clock signal. And the output of the second flip-flop, I'm giving to the next flip-flop. So like that, the output of the mth flip-flop, we are taking as a output sequence, right? The m may be any value, right? Depending upon what is the length you want to generate. So depending on that, we need to consider the number of flip-flops. As I'm saying, there are m flip-flops. So how many states are possible? The number of states are possible are 2 to the power of m. For example, if m is equals to 3, if m is equals to 3, so the number of states are 2 to the power of 3, 8. They are ranging from 0, 0, 0 to 1, 1, 1. So what is the problem here is, so whenever a linear feedback shift register is entering into the 0, 0, 0 state, that means the output of the first flip-flop is 0, second flip-flop is also 0, the third flip-flop is also 0 if I am considering m is equals to 3. That means if I take the state of the flip-flops as 0, 0, 0, if I am using a logic, that logic is a mod 2 operation. A modulo 2 operation or simply a XOR operation. So what happened is that all the flip-flops operation, if you perform the XOR, right? See here, the output of the each and every flip-flops I'm giving to the logic, right? If I'm using XOR operation, right? So if you are using the combinations called 0, 0, 0, the output of the XOR is always equals to 0. That means, so this entire logic is always remains into the 0, 0 state. So it never enter into another state. So it always remains into 0, 0 state. So it is better to avoid 0, 0 state. So how many number of states are remaining now? As I'm saying, the total number of states are 2 to the power of m, and we are avoiding 0, 0, 0 state, all 0 states. So the number of states are now 2 to the power of m minus 1, right? Then, and the PN sequence is a periodic. The PN sequence is a periodic, right? That means the PN sequence periodic means the PN sequence has to repeat after certain length, right? So a PN sequence is a periodic with a length capital N is equals to 2 to the power of m minus 1, right? That means the length of the PN sequence is 2 to the power of m minus 1, right? If the length of the PN sequence is 2 to the power of m minus 1, then that sequence is said to be maximal length sequence. Maximal length sequence. Right? So maximal length sequence means a sequence which is having a length of 2 to the power of n minus 1. Right? So it is not always that it's not required that we need to apply the output of the all flip-flops to the logic. Right? So whatever the logic I'm defining here, I'm saying it is a mod 2 operation or XOR operation. So this logic is a random. This logic is a random. That means you can apply any output of the flip-flops to the logic. It's not mandatory that we need to apply output of each and every flip-flop to the logic. So this logic is a random, and this random logic should be conveyed to the receiver. So it should be known to both the transmitter and receiver, so that whatever the PN sequence we are generating in the transmitter section, the same PN sequence can be generated in the receiver section. So let us see one of the example of this PN sequence. Now we will produce the PN sequence, right? So let us consider a PN sequence of length 3, let's say length 7. That means we are taking 3 flip-flops. So let us consider an example where the number of flip-flops are equals to 3. The value of m is 3. So I'm taking 3 flip-flops here. So let us define, this is the one flip-flop S1. So another flip-flop, let's say it is S2. So another flip-flop, let's say it is S3. So we are applying a clock signal to move the data of one flip-flop to the another. So this is a clock signal. As we know that the output of the data of one flip-flop I'm giving to the another flip-flop whenever we apply the clock signal, and we'll take the output of the last flip-flop as the PN sequence. Right? So let us define a logic here. I'm defining a logic. Right? The logic is like this. So I can apply any combination. I can apply all 3 outputs, or I can take only 2 outputs. So let us say I'm taking the output of the last flip-flop and the output of the first flip-flop or second flip-flop. Let's say a first flip-flop I'm taking here. So this output again I'm storing into the input of the first flip-flop. So this I can call it as a logic. This I can call it as a logic. Let's see what is the operation now. Right? So I'm having here 3 flip-flops, S1, S2, S3. Right? This my output. I can call it as the PN sequence. Right? So what is the input to the S1? The XOR operation of the S1 XOR with S3. Right? I'm storing into S1. As we saying that we need to avoid 0, 0, 0 state. Let's say the initial state is 1, 0, 0. This is my initial state. Right? Now I'm saying the output of the last flip-flop I'm taking as a output of PN sequence. So what is the output in this state? 0. The output of the PN sequence is 0. Now we are applying a clock signal. The output of the second flip-flop I'm moving to the third flip-flop, 0. Output of the first flip-flop I'm moving to the second flip-flop. Now I need to give the input to the first flip-flop. I need to perform XOR operation between S1 and S3. So what is the S1? 1, S3 0, 1 XOR 0, 1. Again I'm storing into the S1. So 1. So in this state the output is 0. Again I'm applying the clock signal. So I'm moving here 1. I'm moving here 1. Right? So 1 XOR 0, again 1. So in this state the output is 1. Again I'm applying the clock. I'm moving the data. Right? So 1 XOR 1, it is a 0. In this state the output is 1. Again I'm applying the clock. 1, 0, 1 XOR 0, 1. So in this state the output is 1. Again I'm applying clock. 0, 1, 1 XOR 1, 0. In this state the output is 0. Again I'm applying the clock. 1, 0, 0 XOR 0, 0. In this state the output is 1. Again I'm applying the clock. 0, 0, 1 XOR 0, 1. Now observe here. So this is the state I'm having here. 1, 0, 0. This is the state I'm having here. 1, 0, 0. Initial state. Again repeating here. So we need to stop here. Right? If you count, how many number of flip-flops we are taking here? 3 flip-flops. the Pn sequence length must be, the Pn sequence length capital N is equals to 2 to the power of m minus 1, where the value of m is 3, 2 to the power of 3 minus 1, which is equals to 7. Right? The length of the Pn sequence is 7. Now just count here 1, 2, 3, 4, 5, 6, 7. The Pn sequence is 0, 0, 1, 1, 1, 0, 1. So this is my Pn sequence. So this is how we need to generate a pseudo noise sequence. So let us consider one more example, right? So let us consider, I'm considering 4 flip-flops, right? Now here the value of m is 4. Here the value of m is 4. So we consider here 4 flip-flops, S1, S2, S3, S4. So we're randomly defining one logic, S3 XOR S4. Now that output I'm again storing into the S1 flip-flop, and the output of the S4 we're taking it as a Pn sequence, right? So initial state I'm considering it as 1 0 0 0, right? We perform the operation until again we receive the state of 1 0 0 0. So as I'm saying, there are m is equals to 4. The Pn sequence length must be 2 to the power of 4 minus 1, which is equals to 15. Now if you count 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, right? Now if you perform again, the same sequence will be repeated because the Pn sequence is a periodic. So I consider here 0 0 1 0 0 1 1 0 1 0 4 ones is my Pn sequence. Now let us see what are the properties of Pn sequence. What are the properties of Pn sequence, right? There are 3 properties for Pn sequence, right? Those are balanced property, run length property, autocorrelation or cyclic shift property. So we will explain all this property by taking one Pn sequence. So let us consider the previous example of the Pn sequence with m is equals to 4. The Pn sequence is 0 0 1 0 0 1 1 0 1 0 1 1 1 1. Right? Now we'll see what is my balanced property. Balanced property or balanced property. Right? In a Pn sequence, if we count the number of ones, right? In a Pn sequence, if we count the number of ones, right? The number of ones are always one more than number of zeros, right? If you count that one, number of ones is 1 plus number of zeros, right? So in this example, if you count the number of ones 1 2 3 4 5 6 7 8, right? And if you count number of zeros 1 2 3 4 5 6 7, here the number of ones are 8 and the number of zeros are 7. So I can say the number of ones are always one more than number of zeros. Why, sir? Right? Why, sir? For example, as I'm saying, it's a random sequence, right? This sequence is even though it is defined with a logic, but this sequence should be appears like a random sequence. For example, so if you are not following this balanced property, let us assume that I'm having a sequence which is all ones, which is all zeros. Now, if you're having a sequence with all ones or all zeros, then I can say that sequence is not a random sequence. For example, right? So you're writing an example. For example, you're writing an exam, right? You're having 2 units, right? Let's say you're having 2 units. For example, if you want to give 5 questions in the exam, right? The 5 questions must be randomly distributed from the 2 units. It should not be like that. It should not be like that. All questions from the unit 1 or all questions from the unit 2. That means directly or indirectly you're conveying some information. So we cannot say it is a random. So random means, right, even though it is defined with logic, it should be looks like a random, right? Now, as I'm saying, the length of the Pn sequence is capital N, right? If you want to find out the probability of ones and probability of zeros, right? In this example, if you want to find out probability of zeros, the favorable number of cases by total number of cases. The total number of cases are length of the Pn sequence 15, and the favorable number of cases are 7 by 15. Similarly, if you want to calculate the probability of 1, right? The favorable number of cases are 8 divided by total are 15. As if I am increasing the length of the n, so what happen? As if you observe the probability of 0 and probability of 1, they're almost equal, right? As if I increase the length of n very large, if I take very large value of n, the probability of zeros are same as that of the probability of ones. That means the Pn sequence is equally balanced between zeros and ones. So that is a property of balanced property, right? So when you observing a Pn sequence, it should not convey any information. It looks like a random. That means there is an equal distribution of zeros and 1. That property we are calling it as balanced property, right? Now let us see another property that we are calling it as a run length property, right? So what is the run length property? Okay, now run means continuous number of zeros or continuous number of ones. The total number of runs in any Pn sequence, the total number of runs are is equals to capital N plus 1 divided by 2. Example, if n is equals to 15, right? The total number of runs are 15 plus 1 divided by 2, which is 8, right? If you consider the Pn sequence, triple zeros, 1, double 0, double 1, 0, 1, 0, 1, 1, 1, 1. As I'm saying, run means continuous number of ones or continuous number of zeros. So I'm having 3 zeros, this is my one run. I'm having a single one, second run. I'm having 2 zeros, third run. I'm having 2 ones, fourth run. I'm having individual 0, fifth run. I'm having individual 1, sixth run, right? I'm having individual 0, seventh run. I'm having continuous number of ones, eighth run, right? So for a length of 15, the total number of runs are 8. Now see here, out of total number of runs, 1 by 2 to the power of n runs are having length of n, length of small n. Let's see, for example, n is equals to 1. Out of total number of runs, 1 by 2 to the power of n runs are having length of n. For example, n is equals to 1. That means the length of the run is 1. Let's see what happens here. So 1 by 2 to the power of n, that means 1 into total number of runs. How many number of total runs am I having? 8. So 1 by 8 is equals to 4. That means 4 runs are having length of 1. If we observe run number 2, run number 5, 6, 7, right? That means 2, 5, 6, 7 are the 4 runs are having a length of 1. Similarly, if n is equals to 2, 1 by 2 to the power of 2 into 8, which is equals to 2. So 2 runs are having a length of 2, right? You see, 3 is a 1, 4 is another 1. So run 3 and run 4 are having a length of 2, right? Let's see another case. If n is equals to 3, n is equals to 3, so that means 1 by 2 to the power of 3 into 8, so which is equals to 1. So 1 run is having a length of 3. So from this example, I can say the 1 run is 3 zeros, right? The run 1 is having a length of 3. Now, if n is equals to 4, right? So, how many runs we completed till now? So, 4, 2 and 1. 7 runs are completed, right? And the total number of runs are 8. So, 7 minus 1. So, if n is equals to 4, so one run is having a length of 4, which is a run 8, right?
3.
So, what is the significance of this run length property? So, let us see, if I am conducting a MCQ exam, right? Let us assume that I am giving 30 questions, multiple choice questions. The question paper should not be like this, should not be continuous number of A's, continuous number of B's and continuous number of C's, right? If you are giving a paper continuous number of A's and continuous number of B's and continuous number of C's, then there should not be any random. So, the runs should be distributed randomly throughout the P-in sequence. So, that is the significance of this run length property, right? So, we will go for the third property. We are calling it as autocorrelation property, right? So, what is the autocorrelation? We are finding similarity between two same type of sequences, right? The correlation is maximum, that means two sequences are having same sequences, right? So let us consider, again I'm taking P-in sequence of same, right? So 3 zeros, I'm taking your 1 0 0 1 1 0 1 0 4 ones, right? Now to explain the autocorrelation property, let us assume that the binary zeros I'm representing with the +1 holes, right? Generally we take -1. So let us consider +1. So 1 I'm representing with the -1. So reverse I'm considering here. So binary zeros I'm representing with the +1 holes. Binary 1 I'm representing with the -1. So it is -1, -1, +1, -1, +1, -1, -1, -1, -1. Right? So let us define this sequence as C of n. Right? And the autocorrelation function is defined as R of d, where d is the delay, which is equals to 1 by n summation, right? Summation C of n into C of n minus d, right? Where small n may ranges from -infinity to infinity, right? Where d is for delay, shifting, right? And assume that there is no delay,